Okay, so how would we simplify this collision operator? Before I go on, I should say that if you really want to do precision calculations in cosmology, of course you don't simplify the collision operator. One can do these calculations at a more exact level. So it's more or less just to get an intuition for what the collision operator does at a more, so to speak, hand-waving level. You don't necessarily need to do all these simplifications, but they are nice and easy to work with, and it's simpler to understand what the equation actually does if you do them. So there are a number of different things that we should be doing in order to simplify the collision operator. One thing which is really important is that we restrict ourselves to looking at processes that have two particles in the in state and two particles in the out state, because that's the simplest possible interaction that you can really have unless you have particles that are unstable and decay. If you have particles that are unstable, then you could have one particle in the in state and two in the out state. But if you have stable particles, then in order to conserve energy and momentum, you need at least two particles in the in and in the out state. You can have more, but you need at least two. And there are also reasons for why you would want to make that simplification. So for example, if we let's just take this Thomson scattering or Compton scattering example that we did before, which looks something like this. Okay, so if you actually calculate the cross-section for such an interaction, again, this is not a field theory course, so I won't go into the details, but just to give you an idea, then the cross-section should always be proportional to something that has to do with the interaction vertex. So when you write the amplitude for the process, each vertex in this particular case gets a factor of a fundamental coupling constant, which we call E. And that means that the amplitude in this case becomes proportional to E squared. But remember, a cross-section is something to do with an amplitude squared. And that means this is really E to the power 4. And we typically normally use not the fundamental coupling constant itself, but rather a dimensionless version of it that we typically call the fine structure constant, which is defined like this. And this is the one that's 1 divided by 137, right, for electromagnetism at low energy, right? So we see this is proportional to alpha squared. Now, if I attach another leg to this diagram, I could, for example, have this double Compton scattering, right? So I have an extra photon that's emitted. That means I have an extra interaction vertex here. So that particular process would no longer be proportional to e to the power 4, but to e to the power 6 and to alpha to the third instead of to the second. And that means since alpha is a small number, and this is true for all weakly coupled theories, that the dimensionless coupling constant is small, it's much less than 1. That means that every time I attach more legs, either internally or externally, to such a process, I make it more unlikely. So unless there are something, symmetries or whatever that forbids a certain order of the process, and then I need to go one order higher, then the lowest order process is always dominant, no matter what I do. And therefore, to some approximation, which is typically very good because we're looking at weakly interacting particles, not strongly interacting particles, but weakly interacting particles, I can stick to the lowest order processes. Now, for example, if I were to do a different type of diagram in which I had quarks and gluons, for example, right, I had a quark and I have a gluon, so I have a corresponding process to Compton scattering, then the dimensionless coupling constant at low energy is certainly not small, it's order 1, and that means that I can get additional gluons emitted, for example, here, which would have the same order of magnitude as the lowest order process. And then I can no longer safely assume that they are not important. So we are restricting ourselves to interactions that are fairly weak, meaning electromagnetic and weak interactions, if we talk about the standard model particles. Okay, so that's the justification for looking only at 2-2 interactions. Interactions that have two particles in the in state, two particles in the out state. So that's one thing. The next thing is that we use, so to speak, classical Maxwell-Boltzmann statistics. So rather than using the real Fermi-Dirac or Bose-Einstein statistics, we will then restrict ourselves to Maxwell-Boltzmann statistics. And that means, for example, that quantities like these should be replaced by just a factor of 1, because in classical statistical physics, there's no stimulated emission and there's no Pauli blocking. So that's a simplification. It's not exact, of course. We are making some relatively small mistake, but we are making a mistake. So we cannot do precision calculations in this way. Then another thing has to do with what we actually mean by equilibrium. And that's quite a complicated story that we don't really have time to go into that much detail with. But if I write out a distribution function in what we know as full thermal equilibrium, then what does it look like? Well, it's very simple. If we take into account quantum statistics, it just looks like this, right? It's either the Fermi-Dirac or the Bose-Einstein distribution. And that's all there is to it, right? The only parameter that controls anything is the temperature of the system. But this form of the distribution function comes with an assumption. It comes with the assumption that we are free to change everything. So we are free to change the energy of particles, and we are free to change the number of particles. So we can essentially, as we wish, create or destroy particles. So the total energy in the entire isolated system, of course, is a conserved quantity, but we can reshuffle everything within those boundaries. And that leads to this form of the distribution function. So that's a classical result that I'm sure many of you know from statistical physics. But there are other types of equilibrium, or pseudo-equilibrium. So there's also what we know as scattering or kinetic equilibrium. And what do I mean by that? By that I mean we have some gas of particles. That could typically be the gas of particles, for example, in this room, where I cannot change the number of particles. That's a conserved quantity. So for example, I could not change the number of nuclei without leaking them out of the system or somehow removing it. I cannot have pair annihilation, for example, of nuclei, right? Because I have no anti-nuclei to annihilate with. So that means the number is now a conserved quantity, but I can change the energy of particles. But that leads to a different type of distribution function. That leads to a pseudo-equilibrium where I get an additional parameter, which is called a chemical potential. So you see there's now one additional parameter that I call mu, which also comes into play. So the temperature in itself is no longer a sufficient parameter to fully describe the system. I need something more. Okay, so these are two different types of equilibrium. Of course, this also implies scattering equilibrium, but scattering equilibrium does not imply full equilibrium. So what we will be assuming is that all the particles that we are looking at are automatically always in scattering equilibrium. So that's the fundamental assumption that we're making. And then one might ask, why should that be the case? And the answer is a little bit hand-waving. Well, it depends on the kind of setting you're looking at, but typically scattering interactions are more efficient than annihilation interactions. I'll try and justify it in the cases that we actually look at, but that's the assumption Dodelson makes, and that's the assumption that is normally made when we do these simplifications of the Boltzmann equation. Okay, so having said that, we're ready to move on, because if I have scattering equilibrium of some sort, then, and I have Maxwell-Boltzmann statistics, then remember that in full equilibrium, this is the quantity that Dodelson calls F naught. That in principle should look something like this, and then with a plus minus 1. But I already said that we're using Maxwell-Boltzmann statistics. So this dies, and that means I can just write it as something that looks like this. Then the corresponding scattering equilibrium, which I now just call F, well, that's almost the same thing, except I now have a chemical potential, and I don't have any plus minus factors here. So altogether, it looks like this. And that's, you can see, means that I can always write the full distribution function as e to the mu divided by t times f naught. And this is not a momentum dependent quantity. And that means, for example, up here, I could calculate n naught, the equilibrium, full equilibrium number density. That's the one that I get by integrating f naught over momentum space. But then I can also calculate the number density of this corresponding distribution. And that's super simple because this is not momentum dependent, which means it can be taken outside the integral. And then it just can be written like this. So I get the same relation here for the number densities as I did for the distribution function itself. So the actual energy distribution as a function of momentum, that's actually not dependent on this chemical potential. That depends only on the temperature. And that's the same for the full equilibrium distribution and for the scattering equilibrium distribution function. So that's a fundamental assumption that we'll be working with. And that means by now we are sort of ready to collect everything. Okay, so the full, and I should also say I have some handwritten notes that I put on Blackboard, which actually does this derivation, right? That means, for example, that something like, let's just write it out. So I'm looking at this process where 1 plus 2 goes to 3 plus 4 or the other way around. So this whole distribution function part of the collision operator, that was the one that looked like this. Which of course is somewhat complicated, like this. That I can actually simplify significantly because these terms are just replaced by ones. Like this. Then this term, that can, for example, be written as and then like this. Oops. But now remember that these are very simple, right? So this is e to the minus e3 divided by t, like this. And the same is true for these. But since I have energy conservation in this interaction, I know that energy before and after must be the same. And that means these are actually exactly the same. So this is equivalent to that. So that makes it quite simple, right? So I can actually write this whole thing out like this. Like this, right? So this super complicated phase space distribution actually becomes quite simple. It's just reduced to this very simple function here. That's the only energy dependent quantity that I have, and that makes life a whole lot simpler for me. Okay. So now we're almost there. So now the whole integrated collision operator, this thing here, that can actually be written out now. So I can, this term here, that's not momentum dependent. That can be taken outside the integral. And I can write this in different ways. I can, for example, write it as n3 n4 divided by n3 naught and 4 naught, because that's the way the chemical potential is defined. And then the corresponding one for n1 and n2. Oops. Like this. And then, of course, I get this long collision integral up to 4, like this. I get my energy and momentum conserving delta function, like this. Okay. Then I get the 2 pi to the 4, and I get my squared matrix element like this. And then instead of getting this whole phase space complication, I get something very simple, right? I get just this term here. It still looks pretty nasty though. And that's where the biggest simplification comes in. That's actually just cheating in the sense that we redefine something. So what one does is to define what is known as a thermally averaged cross-section for an interaction. So this is thermally averaged in the sense that it averages over all particles in the distribution that we're looking at, and then it calculates what's the average interaction times the relative velocity between particles. And the way that is defined is that it normalizes, of course, to the number of particles in the distribution, like this, and then it integrates over everything. Okay, it's the same thing as before. Let's just write it out one final time, like this. Oops. Yeah. Let's see. Pf mu, pi mu, like this. Almost there. And then, oops. Like this. Let's see, are we there? Ah, yes, and then this. Okay, that's a definition of the thermally averaged cross-section. And it sort of makes sense because what it does is it calculates what would the cross-section times relative velocity be in the situation where the system has an equilibrium energy distribution described by a temperature T, and assuming Maxwell-Boltzmann statistics. Then it properly thermally averages this cross-section. But the neat thing, of course, is now that I've written it all out, is that you can see these two lines are essentially identical, except for a very minute difference, which is all related to non-momentum dependent stuff. And that means I can actually rewrite this collision operator in terms of this very simple velocity average cross-section. And then you might say, okay, but that's cheating. And yes, it's cheating in the sense that then I leave the complication to whoever, a hapless PhD student or a postdoc, who has to calculate what this term actually looks like in great and gory detail. And well, we've all done that at some point. You should do it a few times, then hopefully not again. Okay, in any case, if that's the case, then you see you can write this whole thing as n1 naught, n2 naught times the velocity average cross-section. So that makes life very simple. That means this whole big collision operator And of course I should have put 2 pi cubed there, like this. Okay. That I can actually write in a very, very simple way, like this. And then I get the term up there. Like this. And then just this so-called velocity average cross-section. That's the whole thing. This is the final answer to what the collision operator looks like for the Boltzmann equation using the assumptions that I have outlined. And now let's try and see in practice what something like this might actually look like. So let's try and look at it for some particular case. So one case that is often of interest is one where we can have production or annihilation of particles. This could, for example, be electrons, positrons. It could also be neutrinos, antineutrinos, or any other such types of productions or annihilations. And what we'll be assuming is that we have some particle species, let's call it X, and let's assume that the distribution function for a particle species X is equivalent to the one for its corresponding antiparticle, up to some very, very small deviation. That's true for all known standard model particles, for example. If that's the case, then we can say that F1 is equal to F2, which is equal to Fx. Let's assume that whatever this annihilates to or is produced from is something that's in thermal equilibrium. So in full thermal equilibrium. So that's assuming that F3 and F4 are equal to F3 naught and F4 naught. So let's take a concrete case where that certainly would be the case. So for example, an often studied case is one where I have a neutrino and an antineutrino that pair-annihilates. They form a Z boson. That Z boson can subsequently produce, for example, E plus and E minus. Right? So that's a completely standard weak interaction. Now these particles over here, they have electromagnetic interactions. So they have very strong interactions compared to the neutrinos that have only weak interactions. So in that case, we could think of these as 3 and 4, and these as 1 and 2. And then it would be safe to assume that whatever we have over here on the right-hand side is in full thermal equilibrium, because that has electromagnetic interactions of various kinds, right? So that has way stronger interactions. But if that's the case, then we can simplify the brackets that we had before. So remember these ones here, because this now becomes equal to 1, right? Because N3 and N4 are specifically equivalent to this. And that means that we can now rewrite the collision operator in a very simple form. So we can actually write it as this. And I can simplify this further because these two are identical, and that means I can write this as, let's just call it x squared, that's this term, minus nx squared, like this. And that's the final result. And then if I plug in the left-hand side, remember that's the one that looks like this. So then the final form of this Boltzmann equation actually is just this one. So then the next question is, what would it actually look like in real life, such a system? Well, before we move on, let's just focus on this interaction term. Forget about the expansion of the universe. Just put the Hubble parameter equal to 0. Say we're looking at a static system of some sort. And then I have a distribution function that I start out with, and I have an equilibrium distribution. So let's just draw the number density here as a function of time. And let's say this is the equilibrium, like this. Then if I start out with a number density which is smaller than the one I would have in full thermal equilibrium, I could start out having no particles. Then we can go and consult what the right-hand side would look like. Okay, so if nx is 0, then this term for sure is positive definite. This is also positive definite. It controls the strength of the interaction, but it's non-zero as soon as I assume there are interactions. That means I have a positive right-hand side. So I would produce particles, and I would keep producing particles until the term in the bracket goes to 0. And it goes to 0 exactly when I have the equilibrium number density. If I start out, on the other hand, with more particles than I would have in equilibrium, then I start out up here, and then I have a decreasing particle number until I reach equilibrium. So qualitatively, what these interactions do is that they always try to push the distribution function, and therefore the number density, into its equilibrium form. And that's exactly what interactions always do in a statistical sense. They always try to push systems toward equilibrium. And that's what we see here as well. So qualitatively speaking, it's completely simple what happens. What happens is that the interaction term I put in drives the system towards equilibrium. Now the next thing that we need to worry about, of course, is what does it look like in some very concrete cases. So that's the next item.